To understand how atoms work, you really need to know the Pauli exclusion principle, which says that all electrons have to have unique set of quantum numbers. So they can't have the exact same quantum numbers. At least one of the numbers has to be different. The quantum numbers all follow from starting with what the principal quantum number is, or the energy level, what we usually call the energy level. So in this example, we're going to look at the different states, the possible arrangements of quantum numbers that electrons can have in the levels n equals 1, 2, 3, and 4. So the simplest is n equals 1. So we've called this the ground state before, but it's not really one state. So in the more complete theory of quantum mechanics, going beyond the Bohr-Rutherford model, there's this additional information that applies to the electron of an atom, or any electron of an atom. So we're not just talking about hydrogen anymore. But the rules are that you take the n value, subtract 1, and that gives you the L value, or the angular momentum quantum number. And so if n is 1, then L can only be 0. L can never be a negative number. So n minus 1 is 0, and n minus 1 is 0, so that's our angular momentum quantum number. The m sub L number, the magnetic quantum number, can take any value from minus L to plus L. Well, if L is 0, then m sub L can only be 0. And then there's the spin quantum number, which is always the same, plus or minus 1/2. So this n equals 1, L has to equal 0, ML has to equal 0, but MS could be plus or minus 1/2. So this ground state really actually corresponds to two states, which we could write in the electron configuration notation as 1s1, 1s2. So one electron would be in 1s1, and one electron would be in 1s2. Just to make sure this is clear, you got a lot of letters going on. The S corresponds to the orbital, which is the value of L. So an L equals 0 is called an S orbital. Moving on to n equals 2. So if n equals 2, then what happens is our possible values for L increase, because L could be anything 1 less than n or below, but not negative. So that means L could be 0 again, or it could be 1. Now we've already handled L equals 0, so everything here is going to be the same. When L is equal to 0, we're in the S orbital, and there are two possible states. So that stays the same. But for L equals 1, now we have additional possibilities. M sub L could be minus 1, 0, or 1, right? Because it goes from minus L to L. And again, MS is always plus or minus 1/2. So in the L equals 1 orbital, we can have 3 different values of M sub L, and for each of those 3, they could have 2 different values of M sub S. So you could have like 1 minus 1 plus 1/2, 1 minus 1 minus 1/2, and so on. Add them all up and you get 6 states. So now we have a total of 2 in the L equals 0, 6 in the L equals 1, so we have 8 states, which would be the 2s1, 2s2, and then all the 2p's. So 2p1, 2p2, all the way up to 2p6. The p orbital is the L equal 1. All right, so I hope by doing, all 4, n equals 1, 2, 3, and 4, you'll kind of get the hang of how to count the number of states and write down the possible sets of quantum numbers. So one of the questions that you'll get either in homework or on an exam is to evaluate whether or not a set of quantum numbers is possible. So hopefully going through this, you'll be able to figure that out. All right, so now for L equals 3, we have one more possibility for L. It could be 0, 1, or 2. We've already covered L equals 0. That's 2 states. L equals 1 is still 6 states. But what about L equals 2? Now M sub L could be minus 2 to 2. So there's 5, each of which could be plus or minus a half. So we get 10. And then the 10 states would be written out like this. So the L equals 0 are the 3s1 and 3s2. The L equals 1 are the 3p1 to 3p6. And the L equals 2 would be the 3d1 to 3d10. So a total of 18 states. And now lastly, n equals 4. So when n equals 4, L could be anything from 3 to 0. So we've done that 0, 1, and 2 are all the same again. 2 states, 6 states, 10 states. L equals 3, we end up with 14 because M sub L is minus 3 to 3. That's 7 possibilities, each with plus or minus a half, for a total of 14 states. Add these all up, and there are 32 states in the n equals 4 level. And you should be able to see the pattern here. I didn't write them on the sheet, but if I were to write the configurations, there'd be 4s1, 4s2, 4p1 to 4p6, 4d1 to 4d10, and then for the L equals 3, that's called an F orbital, so it would be 4f1 to 4f14.